All right, for this lesson, we're going to be talking about some basic rules of derivatives. In the last lesson, we used what we call the limit definition to find derivatives. In this and the next couple of lessons, we're going to be introduced to several differentiation rules that allow us to find the derivatives without the direct use of that limit definition. So a little bit of a quicker way of finding derivatives. All right, so the first rule that we're going to look at is something called the constant rule. And basically what that says is if you have a constant number, like let's say 7, the derivative of that constant, and this is a new notation, the derivative with respect to x, that's what this stands for, the derivative with respect to x. Derivative of any constant is always 0. So the derivative of 100 is still 0. The derivative of negative 200 is still 0. The derivative of pi, which is a number, is 0. The derivative of e, which is approximately 2.71, is 0. The derivative of any constant, any number, is 0. Because remember, derivative means slope. So if you have a constant function is a horizontal line, and the slope of a horizontal line is 0. So the derivative of any constant is 0. Next important rule is called the power rule. What it says is if you want to take the derivative of any power of a variable x, its derivative is power n times x to that power minus 1. So, for example, if I wanted you to tell me what the derivative of x cubed is, the answer to that would be the power, which is 3, times x to the power minus 1, 3 minus 1. So that would be 3x squared. So the derivative of x cubed would be 3x squared. If I ask you for the derivative of x to the 5th, that would be 5x to the 4th. If I ask you for the derivative of x to the 7th, the answer to that would be 7x to the 6th. Again, you could, if you wanted to use the limit definition, you could, but this saves us some time if we know these rules. So that's one of the rules, is the power rule. Another thing I want you to know and realize is that the derivative of x would just be 1, and I can prove that to you. It's by the power rule. The derivative of x, well, that's x to the first power. By definition, you bring the power in front, so it's 1 times x to the 1 minus 1, so that's 1 times x to the 0 power, and anything to the 0 power is 1, so you get 1. So just remember the derivative of a linear variable is just 1, and also the derivative of x squared would be 2x, but that is power rule. Now we can apply the power rule also to something called the constant multiple rule, and what that means is, like, if I wanted you to tell me what the derivative of, let's say, 6x to the 4th would be, then that would simply be 6 times power, which is 4, so 6 times 4 times x to the 4 minus 1, 3, so that would be 24x to the 3rd. If I wanted you to tell me the derivative of 5x to the negative 2, well, then that would be 5 times negative 2, that would be negative 10x to the, and then subtract 1 from the exponents, that would be negative 3. Another one, it might not look like a power rule, but like, let's say I want you to find the derivative of 1 over x to the negative 3. You could approach this is rewrite this. So just rewrite this with a rewrite this with an exponent by moving it up. So that's going to be x to the 3rd, and the derivative of that would be 3x squared. We'll do another one. The derivative, let's say you had 2 over x to the 4th. You could rewrite that as 2x to the negative 4th, and then take the derivative of that would be negative 8x to the negative 5th. So the power rule is a really good method to use. It even works for for radical functions. Like let's say I had the function g of x is equal to the cube root of x, and I ask you to tell me what the derivative of that would be. What you would do first is rewrite this as a rational exponent, so that would be the same thing as x to the 1/3 power. So the derivative of that would simply be 1/3 x to the, and this is the trick, you have to subtract 1 from that exponent, so 1/3 minus 1 is the same thing as 1/3 minus 3/3. That would be negative 2/3. So that would be the derivative of that function right there. So the power rule and the constant multiple rule, they are all very necessary and needed. Some other rules, it applies to sum and difference. So like if you have f of x is equal to 6x to the 4th minus 3x to the negative 2 plus the square root of x, and I ask you to tell me what the derivative of that is, then you can apply constant multiple rule and the power rules linearly across this function. So I'm just going to simply rewrite this though as so this is 6x to the 4th minus 3x to the negative 2 plus, and the square root of x is x to the 1/2. Now I can take the derivative of that, it would be 24 x to the 3rd plus 6x to the negative 3 plus 1/2 x to the negative 1/2, and that would be the derivative of that function there. A couple other derivatives that are important are derivative of e to the x. Derivative of e to the x is just e to the x. The derivative of ln of x is 1 over x. The derivative of sine of x is cosine of x, and the derivative of derivative of cosine of x is negative sine of x. So that is going to finish up all of the basic derivative rules that we're going to look at. And so you could really just make up your own problem, tie this all together. Let's say I had a function. Let's say I had f of x is equal to 6x to the 3rd. Let me clean that up a little bit. 6x to the 3rd minus x to the negative 2 plus the cube root of x squared plus sine of x minus e to the x plus ln of x. And I ask you to take the derivative of this function, as weird as it looks. Just take it one piece at a time. So the derivative of 6x cubed would be 18x squared. The derivative of negative x to the negative 2 would be positive 2x to the negative 3. I rewrite this as x to the 2/3, and the derivative of that would be 2/3 x to the negative 1/3. The derivative of sine is cosine. The derivative of e to the x is e to the x. The derivative of ln of x is 1 over x. So there would be the derivative of that original function for that problem. So again, a lot of rules, derivative rules you can see of, and there are different problems that you can look at. Sometimes you might have to, again, rewrite some things. For example, let's say that you had a function, so you had 4 over 5 x to the 4th. You could rewrite that as simply 4/5 x to the negative 4. Then you could take the derivative of that function. If you rewrite it first, so the derivative of that would be negative 16 over 5 x to the subtract 1, so that would be negative 5th. So sometimes it's necessary to rewrite things so that you can take the derivative of that. Another type of problem that I want to look at really quickly is finding the average velocity or average rate of change, not to be confused with the instantaneous rate of change. The instantaneous rate of change is your slope. Your average velocity is simply easily just finding slope between 2 points. So for example, let's say that I had an object and I dropped it from a height of 100 feet. So I had some object and I dropped it 100 feet. The function s is equal to negative 16 e squared plus 100 models the distance, the height, s, of that object at any given time, t. S gives me the height in feet, where t is the time in seconds. Let's say I wanted you to find the average velocity, and average velocity, that's the average slope, on the time interval from 1 to 2. Well, it sounds like it's complicated, but it's not. What you would do is you would simply find the slope on this interval. So in other words, what s of 2, right, s of 2 minus s of 1 over 2 minus 1 is, and you can find s of 2. S of 2 would be, if you plugged in 2 into the formula, we get 4, you get negative 64 plus 100, so you get 36, s of 2, and then for s of 1, you would get negative 16 times 1 squared plus 100, so you would get 84 for that. And so then the average velocity for that would be 36 minus 84 divided by 2 minus 1, so that would be the same thing as negative 48 over 1, so that means that it's traveling at a velocity of negative 48 feet per second on that interval from 1 to 2. Negative implying that it's going down, that it's falling. So that's how you find the average velocity as opposed to instantaneous velocity. If I wanted the instantaneous velocity at, let's say, at 2. Let's say at 2. So see, what you found was the average velocity. So on average, that ball is falling 48 feet per second from 1 to 2 seconds. But let's say you want to know what the instantaneous velocity of that object was at 2 seconds. Not more than that, not less than that, just at 2. That would be the derivative. So if you know the function, which is negative 16t squared plus 100, you take its derivative, will be negative 32t, and the derivative of any constant is 0, so it would be negative 32t. Then you could simply substitute the value in for t, so at 2 seconds, so plug in 2, so negative 32 times 2 is negative 64 feet per second. So what's interesting is, on average, from 1 to 2 seconds, on average, the object's falling at negative 48 feet per second. But specifically at 2 seconds, it's falling at 64 feet per second. And you can even test it out at 1 second. So if you took the derivative, which we found was negative 32t, we plugged in 1, we would get negative 32 feet per second. So obviously you can tell that the velocity of the object is increasing. At 1 second, it's falling at 32 feet per second. At 2 seconds, it's falling at 64 feet per second. So, of course, on average, that would be negative 48 feet per second for that. But again, don't get average velocity confused with instantaneous velocity as well. All right, one final problem to look at, and let's say it says using the derivative to find velocity. Let's say that there was a person who was diving and he jumps off of a platform that is 32 feet above the ground, so 32 feet, and that person jumps into the water. Let's say the function s of t equals negative 16 t squared plus 16t plus 32. That models the position of the diver at any given moment in time. So what if I ask you to tell me, first of all, when does the diver hit the water? Well, the diver hits the water when the position is 0, so that's easily solved without calculus, just simply taking the position function and simply setting that equal to 0 and solving that for t. And I notice that I can divide everything by negative 16, so that gives me t squared minus t minus 2 is equal to 0, which makes this easy to factor into 2. So I'd have t minus 2 and t plus 1. Set each one of these equal to 0, so I get two answers. T is equal to 2, t is equal to negative 1. But of course, in the context of this problem, we don't associate negative time. So it's going to take 2 seconds for the diver to hit the water. So now the question is, well, what's the diver's velocity at impact? So how fast is the diver going? Not on average, but specifically at. at t is equal to 2, what is the diver's velocity? Well, that means I need to find the derivative, its rate of change. It's instantaneous rate of change at that point. And so the derivative of that function would be negative 32t plus 16, and then you can find the derivative at that time by simply plugging in that, and then you would get negative 64 plus 16, and then that would give me negative 48, in this context, feet per second. And so I know that on impact, that diver is going 48 feet per second when he or she hits that water, and the negative just implies that diver is going downward in the downward direction. All right, that's it for today's lesson.